Uh, Now I request Dr. Yesu to welcome the gathering and also to introduce the chief guest for this webinar, Dr. Thirugnanam. Please over to Dr. Yesu.
Thank you, sir. A very good morning to one and all present here. I welcome you all for the fourth webinar session on Biomedical Engineering Prospectus and Opportunities. I welcome today's resource person, Dr. A. Thirugnanam, Associate Professor, Head, Department of Biotechnology and Bioengineering, National Institute of Technology, Rourkela. He is our alumnus. With immense pleasure, I introduce Dr. A. Thirugnanam. He completed BE in 2003 and ME in 2005 and PhD in 2011 from IIT Madras. After that, he joined as associate professor at NIT Rourkela. His areas of interest are biomechanics, biomaterials, and biotransport. He has completed 2 projects funded by DBT and SERB. He has published more than 25 papers in peer-reviewed journals. Under his guidance, 9 scholars are doing research. He has guided 11 PG projects and 25 UG projects. With this introduction, I hand over the session to Dr. A. Thirugnanam. Sir, please.
Thank you, Dr. Esu, and I welcome all the participants and students who will be joining today's webinar organized by the Mechanical Engineering Department. Yes, sir.
Thirugnanam, please. Voice is not audible. Please.
Okay. So I'll welcome all the participants in today's webinar speech. I am chosen a topic on biomedical engineering, which is going to be, an odd topic to mechanical engineering department. So when I saw the webinar poster that organized by the mechanical engineering, many people will be wondering why this biomedical engineering is coming forward. Now, coming back to biomedical engineering, people may have thought that who will be taking this biomedical engineering? Are the MBBS people or uh, electronics or instrumentation people or any other branch of people? So in this today's talk, I will be briefing you about a gist of what biomedical engineering is about and what are its prospects and opportunities that are lying forward. So before going into the talk, let me briefly introduce about my institute. NIT Rourkela is in Odisha, one of the oldest NITs, which started in the year 1960 or 61, and it has a large campus with 550 acres and 20 engineering departments are available, 20 departments, academic departments. More than 6,000 plus students are pursuing either UG, PG or PhD, and we have about 1,000 plus research scholars and NIT Rourkela. And its NIRF ranking is 16 for the year 2019, and from the NITs, if you see, it is ranked second after NIT Trichy. So NIT Rourkela has very strong research publications and research output as compared to NIT Tirchi. The only points where we may lose in the ranking is because of the perception where NIT Rourkela is located in a remote area. And most of the people are not aware about NIT Rourkela. Even if I say NIT Rourkela, they think, oh, it is Roorkee. Indirectly they think it's IIT Roorkee. Roorkee and Rourkela are entirely different. Okay, coming back to my department, I am a graduate from, my basic degree is mechanical engineering, and I landed up in this department, which may be a little bit awkward, biotechnology and medical engineering. This department is one among the 20 departments in NIT Rourkela, started in the year 2007, and I joined this department in the year 2011 after serving in Bharat Forge, a forging company which is located in Pune. So I graduated, I was working in the industry for 2 years plus, and then when I got into this system, I thought, should I continue or what is the prospectus? Even I had a lot of ambiguity that if I land into the biomedical or biotech, what will be my future?
Please, sorry for the interruption.
Okay,
Thirugnanam, please hold your mic like this. We are your
okay,
voice is not audible. Sorry, sorry.
okay.
Okay. Okay.
Is it audible now, sir?
Yes, yes.
Yes, yes, yes. Now.
Okay, thank you. So this department offers undergraduate, postgraduate, and PhD programs. We have two programs. One is BTech Biomedical Engineering, and another one is Biotechnology. Biotechnology will be very popular, I think, among you people. Biotechnology is well uh, versed as compared to biomedical. Biomedical engineering is recently emerging field. So we have both undergraduates and postgraduate along with PhDs offering in these two disciplines. This department is FIST, DST FIST sponsored department and also accredited by MBA. We have 5 Center of Excellences in this department uh, and 2 program support. So a lot of funding and a lot of research work is going on. And apart from that, there are also many startups and entrepreneurships done by our students. One example I could give you is we have recently one of our students has started a company called Miraculous, which has won the best startup or entrepreneurship by the government. And they have found a material which will be used to clot blood in 30 seconds. So if a person is injured, so within 30 seconds, if you apply that material on the injury, the blood gets clot. So preventing loss of blood. And this project is also very much appreciated by the DRDO. And now the government of India is planning to, fund further to enhance, enhance the production of this material. There's also other entrepreneurships started by the students, undergraduates and postgraduate students that are running successfully in the TBI of NIT Rourkela. Coming to this department, we have these bottom uh, 6 codings which I have given. It stands for the 6 academic groups what we have, which caters both the biotechnology as well as mechanical engineering department. Medical engineering department. Now coming to the first one, BTE stands for the Biomaterials and Tissue Engineering. MEI stands for Medical Electronics and Instrumentation. BMBT stands for Biomechanics and Biotransport, where I belong to. BPE stands for the Bioprocess Engineering. CMC is Cell and Molecular Engineering, and this one is Environmental and Agriculture. Now, if you look, what will be the role of mechanical engineer? I will say that mechanical engineer has, partly or fully important role in almost all these core academic groups. The first three, the first one in biomaterials and tissue engineering, which one case study I'll be briefing. In the medical electronics and instrumentation group, most of the people from the EI, electronics and communication, electrical, they have a lot of prospectors. Biomechanics and biotransport, the mechanical engineers and chemical engineers will play a vital role. In the bioprocess, again, the mechanical and chemical and biotech people have a major role. Cell molecular, you may think what is the role of mechanical engineers. There's a new subject emerging called mechanobiology and mechanotransduction, where the mechanical engineer's role will also be very vital. And the last is the environment and agriculture, where little bit of scope is there for the mechanical engineers to do. So over a nutshell, if you look at bioengineering, these are the various branches of engineering that comes with the bio engineering. Now, if you look, the mechanical engineering has the biological systems and processes, which is going to play a vital role. Biomechanics and other things will come. Then the chemical engineering, computer, electrical, physics, mathematics, chemistry, and biochemistry, biology, materials and material science and engineering, mechanical, etc. So all has some part of the bio component in it, and it is used in global head, materials, fluidics, tissue, point of care diagnostics, medical imaging, molecular, gene therapy, or systems modeling, or computational, or biologics, and so on. Now, what is biomedical engineering all about? So it's basically the mixture of engineering, technology, and biological sciences, which is responsible for developing, designing, and improving some of the medical devices and other things. Examples: you have artificial limbs or artificial prosthesis, or you can also have some of the imaging machines, which is be useful for diagnosis purpose. So overall, biomedical engineering is a interdisciplinary, highly interdisciplinary field, which is required, uh, or the part of mechanical or other disciplinary will be involved, uh, to develop a common goal, that is to improve the healthcare systems. And this is one of the emerging engineering branch of engineering. As long as human life exists, uh, this is not going to die. And some of the major broad disciplines of biomedical engineering include, but not limited to, tissue engineering, biomedical imaging and signal processing, systems physiology, instrumentation and control, biomechanics, biotransport, and it goes on. Now, let us see what will be the role of the electronics in biomedical engineering. We all know that biosensors, commonly or popularly known as biosensors. So, biosensors are going to play a vital role. Electronics or instrumentation, communication people can slowly develop a biosensor. Now, the basic purpose of a biosensor is to identify and analyze. An analyte may be any component or mixture that you want to find. It may be a blood sample or anything. Then you take it through a bioreceptor, transducer, and then you process, and finally you get the results. Now this cannot be designed until unless you have little bit of knowledge on what your analyte is. So where you need to know little bit of biology, and all these components require some knowledge in your electronics and other things. Now, if you look the biosensor part, the biosensors application includes like prosthetic devices, drug delivery, disease detection, environment monitoring, soil quality monitoring, even in food, toxins, etc. A lot of applications are there. Even we are right now working on, the department is working on the food quality monitoring based on some biosensor. Depending on the color of the food, a food or meat can be expressed or found, or whether it is fresh or it is stored in the fridge. Okay, so these sensors are very much useful in monitoring. In soil quality monitoring, you can determine the pH, what is the dampness or other factors in the soil, which will be used for the agriculture and other purpose. Environmental, similarly, the humidity factors, disease detection, your blood glucose detection. So you just prick on your finger, you take a drop of blood and fix it on the glucose monitoring device. It tells you how much is your glucose level. So drug delivery processes, water like that, it goes on in the bio field. There's another area which is more interesting and emerging is the biomems. So we know what is a MEMS, micro electromechanical systems, which is basically a miniaturized system. Now, biomems is the same miniaturized system for biology and medicine. Some of the biomems include in vitro devices. So there are two types of devices. One is in vitro and another one is the in vivo type of devices. In vitro devices, you use them outside your body for testing. In case of in vitro devices, you will be using those devices inside the human system or any living system. So one such example is on lab on chip. Now, this lab on chip is used for point of care diagnostics, that is genetic sensors, capillary, protein sensors, glucose sensoring, etc. Like I told you, for blood glucose monitoring. So if you go back to this, it includes a lot of electronics part. At the same time, you also know, you should know about fluid mechanics. So fluid mechanics, the mechanical engineering part comes into picture. Now, many of you must have heard, learned or familiar with fluid mechanics, but there's something called microfluidics. The same concepts are used in small capillaries and other things, where you will be designing point of care diagnostic tools for monitoring such type of sensors. Then you have high throughput devices. Typical example is your DNA detection and sequencers or DNA microarrays. Then the last is the cell culture and cell sorting, where people who hardly, or mainly work on the cell or biology part require this. Now, cell culture and cell sorting, mostly the biologist will be using. A typical example is your flow cytometric analysis. In the high throughput devices, DNA detection. Right now, we are very much worried about this COVID-19, and COVID-19 is a virus. It's a RNA type of virus which doesn't have a proper DNA. So what you need to do is you need to replicate those DNA into large amount of copies. So until and unless you have about 3,000 copies, you will not be able to determine whether you are COVID positive or not. So people use a device called RT-PCR, real-time polymerase chain reaction. So the RNA is polymerized to DNA, and it is then multiplied so many times in a real-time PCR to detect. And that's why you take about 3 hours at least to detect a COVID positive test. So COVID test is time consuming, and this RT-PCR is one of the accurate testing methods rather than appropriate or approximate, accurate testing methods through which you can detect this COVID-19 system. Next, there are few applications of microsystems impact in healthcare. You can see right from patient monitoring, uh, the oxygen or your heartbeat, everything can be monitored. Then your IVD testing, that is the typical glucose monitoring devices. The medical imaging, maybe your X-ray, CT, then your patient care for detecting your eye, correcting, earlier days people used to dilate the pupil and the ophthalmology we used to do, but right now computerized testing, eye facilities, drug delivery, where you can incorporate a drug on a material and then you can tailor make that material to allow the drug to slowly release. And you can control the release kinetics of the drug as well. And it is also used in pharmaceutical research as well. So these are very hot areas of field from the electronics and other point. Now, what will be the role of a mechanical engineer in biomedical engineering? So that comes the question. So when you see the biomaterials is one of the areas, though materials engineer, biologist, and mechanical engineer, all three has to, combinedly play some effort to develop a particular material. It cannot be any XYZ material, but it has to be something which the biological system accepts. So biomaterials may be a hard or a soft tissue. If I say hard tissue, it's for bone replacement. If I talk about soft tissue, it is for the ligaments and muscles, which is viscoelastic in nature. So viscoelasticity is another important property which is very difficult to tailor make and to replace or biomimic such type of tissues. Then you have the biological factors, such as the material has to be compatible inside your body. Otherwise, it may lead to some sort of um, you know um, toxicity inside the body. So there are other biological factors like the bioinert or bioactivity or biocompatibility that has to be tested, where a biologist will be used. So it involves cell culture and other facility. Then coming to the design, strength, and durability, where the mechanical engineers play a major role. So designing is one of the most important thing, and we have a small discussion, a case study, where we'll see how the mechanical engineer's role will play. Next is your biotransport. Now, biotransport, again, mechanical and chemical engineers are going to play a crucial role, which involves fluid, heat, and mass transfer in the biological system. So this is in a nutshell, that fluid, heat, and mass transfer in the biological system, where you have a lot of CFD, computational fluid dynamics, the fluid mechanics, heat transfer, and mass transfer can be used. One such example I have given in the later slides. I can elaborate at that time. And the third is the biomechanics, which applies the concepts of engineering mechanics with the fields of biology and physiology. So again, it is purely a mechanical engineer, which has some, will be having some knowledge on biology or physiology, anatomy of human or any animal or living organism, where he can study on the biomechanics part. So biomechanics is a huge topic. So generally, I'll just keep it as biomechanics for a time being. In all these three areas, you can use your modeling and simulation using various softwares. Okay, you have design softwares and analysis softwares where you can use them to develop and design. Now, let us take a simple case study, how to develop what will be the implant design when you want to fix a fracture like this. So you must have heard, if anybody meets with an accident, there's a catastrophic fracture in the tibia or femur bone. Once the fracture is there, the fracture has to be fixed by means of plates, screws, and etc. Now, there are two types of fixation. This figure, what you see is the external fixation, which is very limited nowadays. Nowadays, you do not go or have such type of external fixation. So external fixation means the fixation device is outside your skin with all the screws and nuts and other devices, so that this bone is intact. Okay, and slowly it takes time to heal this fracture region. After healing, there will be a callus formation, and then the patient will be able to walk, and then you can remove all these external devices. This is, a non-convenient process where the patient will be having the external device fixed outside his body until the wound heals. He'll be carrying it, and it's very inconvenient for the subject or the patient. The next technique is the internal fixation, where internally you undergo a surgery, and then you fix the metal plate or screws into the fracture depending on the type of fracture. This is a simple fracture. If the fracture involves large number of pieces, that is crushed or crumble, then you will be having more number of screws fixed along with the bone cement. So this is most popular. Now, when you want to design or you want to choose a material for this fracture, these are the factors that has to be considered. Now, the material which I choose should not be corrosive. It should be corrosive resistant. That means corrosive resistance. Then it should have low modulus of elasticity. I will tell you why. Then it should have high strength to weight ratio. Strength to weight ratio is also discussed. Then biocompatible. This is the biological property that it does not create any sort of toxicity. And then it should also be bioactive or bioinert, depending on the application where you will be using it. Now let's see, based on these factors, which material that you can choose for this sort of problems. We have only three choices nowadays. These are the three materials that you can choose. One is the cobalt chromium alloys. Then the second one is 316SS stainless steel, and L is the very specialist grade which has low carbon. And the third option could be titanium, and its alloys. So among these three, why these three materials? There are also copper, there are also gold, silver used as biomaterials, but these materials are not, um, these materials are having very high strength to weight ratio. Okay, and apart from this, these three materials, titanium and its alloys, are the only material which can be chosen among these three. And the reason for choosing titanium and its alloys are this. Now it has very good corrosive resistance, titanium TiO2. Then you also have titanium corrosive resistance because of this oxide layer. Even cobalt, chromium, and stainless steel, uh, both these material have very good chromium oxide on the surface so that it is highly corrosive resistance. But this TiO2 is very strong, and it will not be so easily, disturbed. The activation energy, or the amount of energy to disturb this TiO2 is very, very large. And at the same time, this material, titanium, is a wonderful material that as you keep machining it, take for example, I do a small lathe cut, skin cut, and remove the outer surface. Immediately when exposed to atmosphere, there is a passive oxide layer formed. This is this TiO2. This passive oxide layer is responsible for the bioactivity of that material. Now, what is bioactivity? The ability of the material to bond with the bone. Now, you are using this material for bone bonding. So, this material should be very good, such that it bonds with the bone very easily, and it doesn't create any sort of complexity or cytotoxicity. So biocompatibility is also a biological factor where it is not toxic. Then coming to the another important mechanical aspect, material property is it should have low modulus of elasticity, or stiffness of the material should be low. So if you take titanium, it's about 110 gigapascal GPa. This probably reduces the stress shielding effect. What is stress shielding? If a clinician uses, say, cobalt chromium or stainless steel, which has higher Young's modulus or stiffness as compared to titanium, what exactly happens is, this is a stress shielding phenomena. So the entire body weight is transmitted to your pelvic girdle and then to your hip joints, kneecap, and it's then transmitted to the floor. Now these are the region where your entire body weight is going to transfer. Now the modulus of elasticity of bone is around 17 gigapascal. Okay, this is the average value that I'm giving, 17 gigapascal. Now this 17 gigapascal is very less as compared to stainless steel or cobalt chromium, which is much higher, like more than 200 plus. Okay, so what happens if there's a mismatch in modulus of elasticity between the bone and the implant? Now, going back to the other slide, if I have a material fixed, my bone's modulus of elasticity is 17 gigapascal, and the implant's modulus of elasticity is around, say, 110 or 210 to 10 gigapascal. There's entire mismatch. Because of this, stress shielding occurs. Stress shielding means that the entire body weight is transmitted to your bone. In this case, you have the hip prosthesis. The blue color, what you see here is the hip joint. Okay, so it gets transferred to the hip joint metallic implant, and this part of the bone is not experiencing any loading, and the lower part of the bone has more load because the entire load is transmitted towards the hip joint and then towards the lower part of your femur bone. So this becomes more dense because bone adapts to its loading conditions. So if you start loading bone every day, then the density of the bone becomes more. There's a Wolff's law, which is defined or described in Wolff's law. And this part, the density of the bone is very poor. So therefore, you want to avoid, from the design aspect, you want to avoid using a high modulus of elastic materials. And you should try to bring the modulus of elasticity almost near to that of bone. Now, till date, there is no such material available which has very good strength. These three materials have very good strength to weight ratio. Why? I'll tell you, because whenever you walk in the dynamic condition, you need to have at least 10 times the body weight. 10 times the body weight is required to withstand when you use a hip prosthesis. It all depends on the dynamism of your walking, how fast, uh, how fast you're going to walk, then what is the cadence, that means the rate at which you walk. If you're walking on an inclined surface, then your body weight is going to act more on this joints. If you're going to climb on a staircase where the stair steps are larger and higher, then again the body weight is going to increase. So all this is again study of biomechanics, which is another part which should be also considered while designing this implant. Now, what happens if I use a larger modulus of elasticity material? Stress shielding occurs. In stress shielding, bone starts to resorb. Resorb means it starts to lose. There are three types of bone cells, osteoblasts, blasts, and cysts. So this bone cell slowly starts to resorb, and once the bone resorbs, the implant will start to loosening may take place. So it causes pain to the patients, and if required, another revision surgery is needed. So to avoid that, you have to choose a material, and so far till date, this material seems to be very good. And when I say titanium and its alloys, there is something called beta titanium alloys, which has Young's modulus approximately to 70 gigapascal, which is more closer and can minimize the stress shielding effect. So apart from all these factors, titanium is also used because if a patient is having titanium implant in his body, later if required, he can be done MRI scan without any problem. Whereas if you use 316 or cobalt chromium where there is iron content, then while performing an MRI scan, there's high chance that that material or the magnetic radiation imaging may influence and try to damage the soft tissues. Also, once you fit titanium in your body, you don't need to do a revision surgery to remove it. Whereas if you have 316 stainless steel or cobalt chromium, you need to perform a revision surgery after 2 years to remove the implant. For titanium, you just need to fit and forget. Now, let me quickly go to some of the design aspects of how to develop the hip prosthesis. From the design point, everybody has different dimensions. So how to get the dimensions exactly what you require. So what they do is, first step is do a CT or MRI scanning, and they get the CT data of the femur. Then from the CT data, they try to compute the solid modeling from the data, and from the solid modeling, they'll do the finite element analysis. So let me show you the two techniques. There are two ways. One is direct, another one is reverse engineering. In direct engineering, first you get a design, then from the computer model, you fabricate and make as a product. In the reverse engineering, it's the reverse way. You take the product, that is the bone, then go for CT scan, and then go for computer model. So there are two types two approaches, the direct and the reverse engineering approach. And what you get from the CT or MRI is thin slices, because it's a topography image. So you get all these thin sizes. You need to stack them like this, then develop the solid model. And from the solid model, you can predict what should be your implant dimensions, and accordingly you can machine. Even a slight deviation in the cross section could cause a lot of injuries to the patient. So to exactly know what is going to be a cross section, these are like three different hip prosthesis stem where the cross section varies at three different in the same location. So the right fit you should get. So again, the mechanical and CAD is required from the orthopedic surgeons to figure out what is going to be your exact dimension, and that has to be manufactured. So for manufacturing the hip prosthesis, you can use any type of conventional or non-conventional, which is more preferred to get very close tolerance and accuracy. So this is a typical CT image. Like that, you keep stacking on this, then you draw the model. So these are the steps involved. First, you get the segments of the CT image. Then the segmentation of the desired objects are made to the Hounsfield number points. And then you create the sectional curves using key points. And then you create a the surface model from the curves. And then you will develop the solid model. Some of the other applications where biomedical is like you can use your CFD, computational fluid dynamics, coupled with structural to find out like what is going to be the flow in your arteries or veins or trunk, etc. So what we do here is this is a small cross section done to reduce the simulation. This is done by a team in Australia. They have taken a symmetry. So once you take symmetry, the other side is also anticipated that it's going to be the same. And they have simulated to see what will be the internal shear stress, flow properties, etc., using the CFD, computational fluid dynamics. So other areas where the electronic people can use in biomedical using this modeling and simulation is you develop a skull. Then nowadays people are using mobile phones very often and speaking over the phone for a long period of time. And it is going to have an hazardous effect, that is your specific absorption rate, the mobile radiation that comes out from the mobile is going to affect your ear and other parts. You can also see the electromagnetic radiation effect of mobile phone and what's going to be the temperature. Okay, so you can just modulate and simulate such type of interesting studies can also be done. And these studies are done using ANSYS. And this is a typical, I've zoomed the ear part. The meshing is large, globular. You can make it smaller because this is going to be your area of interest. So you can start doing a fine meshing. And after fine meshing, you can do the analysis and then study. So the next part which I'm going to brief you is the biomechanics. Gait analysis is a part of biomechanics that is studied, which is used widely by the physician or clinicians to judge whether a person is perfect or not. Now, what is gait? Human gait refers to the locomotion achieved to the movement of human limbs. This is the layman's way of telling, like generally gait means human locomotion. And what it is defined as a bipedal, biphasic forward propulsion of your CG, in which there are alternating sinus movements of different body segments. So as you start walking, your limbs, then your trunk of your body has to move forward. And it is perfect for a healthy person, but for a non-healthy person, if he is having any sort of abnormality, it immediately reflects in his gait walking pattern. So most of the people, what they do is they look at the gait walking pattern of a person and decide whether the person is normal or abnormal. And this gait is used in various applications. Now let me tell you what is a gait. Now look at this person. This leg is the right foot. From the right reference foot till the same right foot touches the ground. This part is called as one complete gait cycle, 100%. In that one complete gait, you have two phases, stance phase and swing phase, where stance phase consists of 60% and swing phase consists of 40%. What is stance phase? The reference foot, that is a blue color foot, which is grounded on the floor, is called stance phase. What is swing phase? The reference foot, which is in the air. So from this point, this is a reference foot, which is out of contact from the ground and it moves forward. till it strikes the heel is called string phase. And there are various subphases explained here. So a normal person should have perfect gait cycle. Now, how do you measure this? This gait cycle can be measured in a 3D motion analysis system lab. So the Department of Biotechnology and Medical Engineering at NIT Rourkela has this 3D motion analysis system lab, which is equipped with cameras, and you have a ramp or where you'll be having the force platforms grounded. So these are the force platforms. So the force platforms measures the ground reaction forces, that is the kinetics. And using this motion analysis system, you will be fixing some anti-reflective markers. So what you see here is the white spots are the markers that are fixed on your anatomical locations in your body. And then you perform an activity, maybe walking or any sort of activity. These cameras will capture. Okay, so what you get is, as you walk, these cameras will only capture the markers, which is fixed in your anatomical position. From these markers, using the link diagram, you'll draw the link. And from the link, you can develop your skeleton model. And from the skeleton model at various joints and locations, you can easily calculate the kinetics and kinematics of a person. So where are these systems applicable? Now, post-surgery analysis. Say, for example, you have undergone a hip replacement surgery. If the surgery is perfect, healed, everything, the patient after surgery is allowed to walk. And from his walking pattern, whether he is back to normal or not, can be easily found out from his walking gait pattern. This sort of system, force platform, is also used in designing the orthotics or shoes. Good companies like Nike, Reebok uses the force platform for designing their shoes. Then it is used for physiotherapy and rehabilitation engineering. It is also used in sports person, highly used in the sports department to study the performance and improvement of sports person and also prevent injury. Another area, the biotransport. In that biotransport, one small area is cryosurgery, which is widely used to ablate tumor. You know, the name itself says cryosurgery, means you'll be using a cryogen, typically liquid nitrogen, and that is sprayed on a particular region of the skin. If you have malignant skin tumor, so it is sprayed on the skin, and then once you spray on a particular location where there is a tumor available on the skin, it freezes the cell. So as the cell is freezed by the cryogen, it destroys the cell. How it destroys? Because cell contains water molecules. Okay, so once the water molecule is freezed or frozen, then it starts to expand. By means of expanding, the other parts of the cell gets ruptured, and in the process, it is killed. So it is very easy technique to remove cancer, and this is widely used in other techniques. So this is the mechanism, what exactly happens. So as the water freezes the hydrogen bonds by spraying of liquid nitrogen or cryogen on the skin surface, then these hydrogen bonds, which are unstable and loosely packed, okay, it forms ice. Okay, once it forms ice, then all these hydrogen bonds are equally bonded, and as a result, the volume of the cell starts increasing, and the hydrogen bonds are more stable in this case, whereas in case of normal liquid cell, it's very difficult. So that's why sometimes for preserving, you also use cryopreservation for preserving some of your cells for further later applications or use. I'm going to other areas. I have only chosen very few topics, and this biomedical engineering is so vast that any branch of engineering can be coupled or can be worked with. The emerging area is the mechanobiology and mechanotransduction. Is a very new area where people want to study about how the cell interacts with each other using the mechanical signals and other things. Then nanotechnology is another area where the same technology can be used on the implant, which I have shown you earlier, to make the bioactive or to improve the bioactivity process. So if you improve the bioactivity, the yielding or the healing time of the patient is drastically reduced using nano. And also you use nanoparticles for enhancing imaging techniques, whether to diagnose cancer cells in your body or to diagnose any tumor. You use this in the as a non-invasive technique method. Then paper-based diagnostics is the lab-on-chip type, where the microfluidics is used to detect healthcare. Then adaptable prosthesis, heart cells, biomimetic materials, miniature cell culture, synthetic, it goes on, and this is only few and it is not completed yet. So some of the wide areas that is not much explored in the country and globally is like mechanobiology, biomimetic materials, diagnostic devices. So most of them are not that much exposed. Now looking to the opportunities of biomedical engineer. In India, most of the bioengineering or biomedical engineers think that biomedical engineering is nothing but an electronics communication or instrumentation. So if you look at the syllabus, what is framed in most of the other universities offering biomedical engineering, it's almost like 80 to 90% something related to the electronics part. But here we have slightly different, that it has all different parts, as I mentioned in the previous slide, from nanotechnology to biology, chemical, metallurgy, mechanical. And if you look at the curriculum abroad also, there's huge amount of interdisciplinary work done on biomedical engineering part. So most of the students who pursue BTech, biomedical engineering, they have ample opportunities for the masters and PhDs abroad with full funding. And if you want to pursue in India for masters and other things, then you need to have some certain exams are there you have to do, which I'll show you in the conclusion part. Then other potential companies, these are the few important big companies that hire biomedical engineers like L&T, General GE, Healthcare, Stryker, Detroit, Texas, Philips, Orbis. These are some of the most important companies that they are hiring biomedical engineers. Apart from that, many hospitals and small-scale industries have developed in our country. And in our country, in India, biomedical engineering is still in the infant stage. So hoping that in next 5 to 10 years, there's going to be a drastic change. So as the time given to me is like limited for 50 minutes, I'll quickly go through the summary that the biomedical engineering is an emerging interdisciplinary field. And the ambiguity which I had in joining this department earlier, thought that I should leave this and join into my parent department, mechanical. Then after staying here for a couple of years, I got interested to work across the interdisciplinary field. So ample opportunities for higher studies, research with full funding and fellowship is available in this stream as compared to the other conventional branches of engineering. So according to the US Bureau of Labor Statistics, it is projected that the biomedical engineering jobs will be between 16 to 26 is almost 7% growth, which is very high. And the demand for biomedical engineers and the pay for biomedical engineers is on very high rated in the Western country. Now, in case in India, if you want to pursue biomedical engineering in undergraduate, a student has to crack JEE Main or Advanced and apply through JOSA for admission through the central funded or IITs or NITs. And for postgraduate, should have a valid GATE score and he should apply through the CCMP to pursue an admission. So for PG students with GATE score, the MHRD gives them fellowship amount monthly as well. So with this, I conclude, and I also put a note that our department looks for internships, CRF, SRS, and research students, who are very much interested to work. And for any details or anything, you can contact me with this email ID. And with this, I thank you and thank the KCG College for giving me this opportunity. Thank you for your attention.
Thank you, sir. One or two questions from the participant side. One question from Mr. Yuvraj. Can you elaborate the role of contact mechanics in biomechanics?
Contact mechanics.
Yes.
Okay, so what I understand is contact mechanics is when you have the foot grounded in your flow. Okay, the foot. If you go back to the force platform, there are two equipments. Force platform, the one which you see here, is basically a force platform. It's basically a force transducers made up of strain gauges or piezoelectric crystals. When your foot is landing on this, based on this contact points, where a pressure point is there, it is very much useful to design your orthotic devices or shoes. Okay, so there are pressure sensors, and accordingly, the sole of the
Hello.
Yes, sir.
Sir, it's not audible. Hello. Hello.
I think muted.
Okay. Uh, Sir, is it audible for you, sir? Hello.
hello.
Is it audible for you, sir?
Yes, it is audible for me.
There is one more question, sir. What
Yes.
are the facilities available in your campus? Whether those facilities can be utilized by our students who are doing projects in biomedical field?
Yes, we have a CIF. You can go to the CIF, stands for Centralized Instrument Facility. It is almost similar to the SAFE, Sophisticated Analytical Instrument Facilities. So through CIF, you can make a request, and those facilities can be utilized.
And one more question. Um, our students did some projects on prosthetic limbs, but they are not able to proceed further because of the lack of facility. I think they have printed using 3D printer, but later that was not further. The project is not extended. So, what do you suggest, sir? How to go further, sir?
Okay. So you need to once you make the product using 3D printer, you need to test it or validate it. So for validation, you need to choose a lab where you have this motion analysis, okay, and ask the concerned patient who's having the disability, or the subject is having the disability to walk on these limbs, and then you need to correlate the data for commercializing or next stage, whatever you want to take forward.
Finally, sir, what do you suggest our student uh, about after completing their BE mechanical engineering? How the interest should be created to join in biomedical field, and what is the improvement when compared to other fields if they join biomedical fields?
See, there are two things that students normally think. Once I graduate, I should get a good job with high package. They'll be comparing with the counterparts in CS or EI departments, where he is able to get more, like Google gives you, Adobe gives you so much. But this field is entirely different. If you have passion and interest, and there is a lot of skills or applications of mechanical engineering that can be explored in the biomedical engineering. The list of institutes is available in the CCMT site or JOSA site. They can visit, and or another option is to pursue higher studies abroad. In abroad, the funding is more as compared to our country, and there's a lot of opportunities that flourish.
Thank you, sir, for
Sir,
answering our
sir.
questions.
Yes, sir, sir.
We
Yes,
request your continued support for our students. Sir, what do you want to tell, sir? Yes, sir.
yes, sir, sir. Few more questions in the chat box, please, sir.
Just a minute, sir. Uh, Sir, one question from Sheshwan. For biosensors, what are the real-time application used in our daily life? Sir, it is not audible, sir.
Twice.
Yes, sir. Yes, sir.
Okay, that is one example. Another example could be your pregnancy test kit. The pregnancy test kit is also a sort of bio device which is developed on a lab on chip. So you just put a drop of urine on that, and it immediately gives you the mark. So these are some of the typical applications of biosensors.
One participant requested you to share your screen, which has the contact details, sir.
Last
Your contact
slide.
details.
Last slide. Ah.
I hope that the participant is making a note of it.
Okay, sir. We can conclude, sir.
Sir, thank you, sir. Thank you for answering our
you.
questions. And also, we request you to continuously support our students of KCG College. Now, I request Professor Kannan to propose the vote of thanks.
Okay. Good afternoon to everyone. On behalf of our management, we thank Dr. Thirugnanam, Associate Professor and Head, Department of Biotechnological and Medical Engineering, NIT Rourkela, for sharing us the various opportunities in biomedical engineering. His insight into the field was very different and ignited our spirit of many to pursue biomedical engineering. We thank you, sir. Also, we thank all the panelists and participants. Hope we all had a nice sections. Thank you all. Thank you very much, sir.
Thank you very much, sir.
Thank you.